Here we have the 2020 projectiles question. Question 3b. A plane is inclined at an angle 45 to the horizontal and a particle is projected down the plane with initial speed 2√2 at an angle 45. So let's write that down. 2√2 cos 45 in the I direction plus 2√2 sine 45 in the J direction. And that works out to be cos 45 is 1/√2 as is sine, so that's going to give 2i plus 2j for my initial vector here. Now we have to consider the accelerations. Now we're dealing with 45 degrees here, so the acceleration will be the same. Just one's positive. It's positive going down the I-axis, the incline being the I-axis, and it's negative in the J direction with G pulling down towards the Earth. So we're going to have G, it doesn't actually matter whether it's cos or sine 45, but it will be G sine 45. We set up our diagram consistently in the I direction, and our acceleration in the J direction will be minus G cos 45. So G over √2 for A and minus G over √2 for A. So what are we told here? We're looking for D. Find the value of D. And here's D here at this point. And then there's another bounce, and this is K times D. So let's look at the displacement in the X direction or the I direction. UT plus a half AT squared, which is equal to my initial 2 times T, and then plus a half times acceleration, which is G over √2 times T squared. So we can just tidy it up a little bit. 2t plus gt squared over 2√2. So that should highlight that we need t. So the displacement in the y direction will be equal to 0 at this point here and at the beginning, these 2 points. So let's find out when that is. Displacement in the y direction is ut plus a half at squared. So my u again 2. So 2t, my a is going to be minus, so minus 1/2 by g over √2 by t squared. Factoring out my t and allowing it to equal 0, we're going to get t times 2 minus gt over 2√2 equals 0. So my initial time equals 0. And then we're going to have gt over 2√2 is equal to 2. So cross multiplying, we're going to get 4√2 divided by g equals t. So we can sub that back in over here. We're going to get 2 times 4√2 over g plus g times t squared. T squared, we could write it here just separately. T squared is 16 times 2. 32 over g squared. So g times t squared is going to be g times the 32 on top and on the bottom the 2√2 and the g squared. So tidying this up a bit, these are all just numbers, but we're going to get 8√2 over g plus 16. The squared will cancel with the g on top, so we're going to get 16 over √2g. And we tidy this up by cross multiplying. I'm putting √2g squared on the bottom. So we're going to get cross multiplying 8√2 by √2g, which is 8 by 2 by g, 16g. On the other side, it'll also give 16g. So we're going to get 32g over √2g squared, being displacement in the x direction, which is equal to d, and on a calculator this gives 2.31, and we're dealing in meters, and obviously we could have cancelled the g on top of the g squared in the bottom. I'm sure you did that. So this is d. Then there's a second bounce. So the coefficient of restitution we're given here is 0.4. The range of the second hop is kd. So we need the velocities before impact in the I and j direction. we need to then apply our new velocities with e included for the j, and the I doesn't change. That should enable us to find the value of k. So let's start with the v's. So v is equal to u plus at. So let's start with the I. The velocity, when it started at 2, it has accelerated at g over root 2 for a time of, what do we get for time? 4 root 2 over g. From down here, when it hits at impact, this is going to be the velocity. Velocity is going to give 2, and there's a lot of cancellations, just leaving me with a 4. So that's going to be equal to 6 in the I direction. For the j, we're also going to have 2 to begin with. 2, and then it's minus g over root 2 times, the same time, 4 root 2 over g. So we're going to have 2 minus 4 on this side, which is equal to minus 2j. So my new velocity vector is equal to 6i minus 2j. That's an equals. Now applying minus e to the j component, we have to multiply by minus e. Our new velocity vector will be 6i minus 2 by minus 0.4 in the j direction. So after impact, it's going to have a velocity of 6i plus 2 0.4s, or 0.8 in the j direction. So s of x is equal to k times d. So we're going to need the time taken for it to go from the first bounce to the second bounce. So again, s of y will be equal to 0. So let's say s of y is equal to ut plus a half at squared. So my u is 0.8 times t. My acceleration will be the same, minus g over root 2 times t squared. So factoring out the t, we're going to get 0.8 minus gt over root 2. Just let out the half, so 1 there and 2 there. So just have it's g over 2 root 2. That's equal to 0. So I have my initial time equals 0. And this one here is going to give me 2 root 2 by 0.8 is equal to gt. So dividing all this by g, 2 root 2 by 0.8 divided by 9.8, t is going to give me 0.23089. Might round that off to 0.234. So let's continue from here then with s of x. We know the time taken, t is equal to 0. I'm going to actually, you know what, I think I'll leave it at 5 decimals. Just for now, we'll round it off at the end. There's no point in rounding it off too early. S of x is equal to ut plus a half at squared. So we have s of x is our 6. Just double check, yeah, 6i, 6 by 0.23089 plus a half by a, which was g over root 2, by t squared, which is 0.23089 squared. So they're really testing your patience in this question. So the displacement in the x direction, which is equal to k times d, is equal to, on a calculator, it's coming out at 1.57. Well, we have 2.31 for d, so I think I'll round it off at 1.57. So we got d to be 2.31. Yeah, d just there, 2.31. So 2.31k equals 1.57. So k is equal to 1.57 divided by 2.31. So k is going to give 0.679. I think I'll round off to 0.68. And that's this question complete.